Okay, so I think we are on. Welcome everyone for those joining us from YouTube and LinkedIn. Just a quick check because at the moment no one is commenting. Can those on YouTube or LinkedIn just type yes if you can hear us and see the slide on the screen? I mean the tiny note. I know there is a bit of latency, but it's okay. There's definitely people registered because I could see that on the thing.
All right.
Registration. YouTube, please say yes. You can hear us, see us, and see the most importantly the notes on the screen. Let's see. We do it all the way just to check on YouTube. Yeah, it seems like we have 2 people on YouTube. Those on YouTube, please ping us so we are sure everything is okay. You can hear us. Yes, thank you, Michael. Perfect. Yeah. So before I hand over to Adrian, I'll just share this resource that I think it's going to be very useful for you guys, especially the ones interested in machine learning stuff. Let's see, share screen. Yeah. So can you see? I don't know if they can see this fantastic repository by Bruno Gavranovic. I think this. Let me just paste it. You can also Google him, and you'll find it. He has very amazing resources on category theory itself. A lot of resources. Notes, lecture notes, video lectures, and these things, just to supplement your what you are going through with Adrian. Because in reality, this session meant to be like ask me anything. So but Adrian has been very nice to reviewing the basics. But I definitely recommend you guys to go through over these resources. Those of you interested in machine learning stuff, there is a lot of useful resources here that you could leverage, in order to see how powerful a category theory as a framework can be. And this is emerging, right? Because not many people are really working on this. And this by itself, those of you looking for career opportunities and this type of stuff, this could be a very nice thing to look at. And those of you who are interested in doing a project on this, some things, you could, we could possibly find you a mentor, a mathematician to mentor you on this. So that's it. I'll stop sharing. And Adrian, thank you again for joining us. And everyone, good luck with the session. Well, I don't think I need to say good luck, but enjoy the session. That's what I meant. Yeah.
All right. Thank you everyone for showing up again. So as in the last 2 times, this is essentially like a TA session where you can just ask me whatever you'd like to ask. But if I don't get any questions, I'll just carry on expounding a little bit about the basics of category theory. And I'll take your questions as they come up. So in the very first Ask Me Anything session, I told you what a category is. I first gave you an informal definition, saying that a category is what you get when you have informal category is what you get when you have some sort of object of the same type and some sort of way of going between these objects, and when these ways of going between the objects are composable. And then I tortured you with this rigorous definition of what a category is. And then we defined what a functor is, and we spoke about how any monoid can be viewed as a category, and how any set can be viewed as a category. And we were able to do the sanity check and note that a functor between categories reduces to a morphism of monoids for whenever you view a monoid as a category, and reduces to a map of sets whenever you view sets as categories. And then finally, in the very first session, I raced through what it means to have a natural transformation between functors. Then in the second Ask Me Anything, I reviewed natural transformations again, and I motivated the natural transformation from the point of view of homotopy theory. Right, so I started off by telling you about currying. So whenever you have a map of sets, from x plus y to z, that's the same thing as having a map from x to maps from y to z via this correspondence. And something similar is true for categories, where functors out of the product of two categories into a given categories is the same thing. It's supposed to be the same thing as functors out into the functor category of functors from one category, the category of functors from one category into the other. And just by using this principle, we're able to figure out what exactly the data of a natural transformation is supposed to be. Right, so we noted that there exists this category with exactly two objects, 0 and 1, and a single non-identity morphism going from 0 to 1, which I'd noted iota, together with the two identity morphisms. And we observed that a functor from this category with exactly two objects and one morphism into a category is the same thing as picking out a morphism. So via this Howard correspondence, we figure out that a morphism between functors is supposed to be the same thing as a functor out of C cross I into D. So I is this category here. So we took this idea seriously, and what we discovered was that whenever you have two functors, f and g, going from C to D, then the data of a natural transformation from f to g is the same thing as for every object C0 in C, you get a map in D from FC0 to GC0. And then whenever you have a square like this, so for C1, I also get a map from FC1 to GC1. And because f is a functor, I get these vertical maps. And I have a square, and I can ask for this square to commute. And someone in the audience asked me how this gives us a category. Right, so I've already told you I'd already told you what the objects of this functor category are, the objects of the functors, and I told you what the morphisms are. They're these natural transformations. So all we need to figure out is how to compose them, and you basically do that in the obvious way. Whenever you have a map C0, you have a natural, part of the datum of a natural transformation is a map from FC0 to GC0, and from GC0 to HC0, and then you have to compose these morphisms. And one thing you should also check to see that you really get a category is you should check that you have identity natural transformations from any functor to itself. So if you take G to be F, then just the identity morphism everywhere will give you the identity natural transformation. And after that, we checked rigorously that all of the examples in the beginning of the very first AMA that we in fact get categories. So we checked that topological spaces are categories, that topological spaces form a category. We checked that groups form a category, and and the left it as an exercise, the vector spaces form a category. So today we will finally talk about universal properties. And this goes, and that, to understand universal properties, what you there are basically two ways to approach universal properties. There's one via initial and final objects, and there's one via representability. And I will start off with the one involving initial and final objects, because I think it's this approach is easier. All right, so so we now have a chapter, universal properties, and we go to section, initial and final objects. All right. So I can just start off with the definition of an initial or a final object. So definition, let C be a category. Then an object C and C is called initial or final if for all other objects in C, or for all C prime in C, there exists a unique morphism from C to C prime. In the initial case, or there exists a unique morphism from C prime to C. All right. So let's have a look at some examples. So let's look at the example of the category of sets. So recall that the category of sets has sets as objects and maps of sets as morphisms. So I want to figure out what the initial object is and the final object. And the final object is usually a bit easier. Does anyone have an idea what the final object in the category of sets is? So we want to find a set such that for any other set, there is only one map to this set. Right, so a final object is given by any singleton. So what I've written here, so whenever you write a set, you often use curly brackets. So this here is the set containing three elements, A, B, and C. And so here I have a set with only one element, but it doesn't matter what I call this element, right? I mean, this is the same thing as, so I'll tell you what this funny looking equal sign means in a bit, right? You can also have it be one or some set containing a single elephant or something. So this is supposed to be an elephant or whatever your favorite animal is. Right, and this is the final object, because for any other set in X, so if X is a set, then, well, let's try to write down a map from X to a final object. Well, if small x is an element of X, where can I send it? Well, I don't have a choice. There's only one element I can send it to. I can only send it to star. That's my only choice. And because I only have one choice, then there exists a unique set, a unique map. So I see in the comments that two people guessed the initial, the empty set. So the empty set is indeed the initial object. So, and here you'll see something else, which is that for the final object, so I'll hopefully get around to today to tell you why I'm always using the definite article when I'm talking about the final object, when I say the final object and not a final object. At this stage, I should always be saying a final object. So here we have a final object. There are many choices in a set theoretical sense for a final object, but the initial object is genuinely unique. So from the point of view of set theory, there's only one empty set. And so how do we know? No, so Michael is asking if there's more than one constant map. There's only ever one constant map. So to any one of these sets, there's only ever one constant map. But there are many choices of sets with only one element in it. Does this answer Michael's question? So let me turn on the light while I'm waiting so that I'm no longer shrouded in mystery. A bit too much light. There we go. All right. But in any case, there's only one empty set. And to see that there is only one map from the empty set to any other set, we need to be a bit pedantic. Right, so so recall that a function, a map from A to B is set theoretically given by its graph. So it's given by a subset of A cross P, such that for all A and A, there exists a unique B and B, such that A comma B isn't gamma. This is literally what it means to have a function. This is the definition set theoretically. So if we try to play this game now here with the So if we try to play this game now with the empty set, then we're looking for some subset of the empty set cross X. But the empty set cross times X is just the empty set. And the only subset of the empty set is the empty set. And all elements of the empty set have all properties. And therefore, gamma must be the graph of a function. If you're not very comfortable with set theory, this argument will seem a bit nonsensical, but this is the rigorous way of doing it. Otherwise, you can just take it as a definition that there exists exactly one map from the empty set to any other set. So let's move on to the example of groups. We had the example of sets. Let's move on to the example of groups. And again, let's think about the final and the initial objects. And I'll again start with the final object. Does anyone have a suggestion for what the final object is, or a final object is? Right, so the final object is a group often just called one, and as its underlying set, it only has one element. And well, we know about any group that any group has an identity element. So this one element has to be the identity element. So it does turn out that the group with only one element is a Lie group, but this is not necessarily super relevant for well, Lie groups are more than just groups with properties. They're group with structures. Right. So Michael writes E. Exactly. So recall that a groupomorphism is a group between the underlying set, is a map between the underlying sets of the two groups. So whenever I have another group, then we already know from above, right? We know already from here that there exists only one map between the underlying sets of G to the underlying sets of 1. And all we have to do is check whether or not this is a group homomorphism. And the right, so what we need to check? We need to check that the identity is sent to the identity. Well, the identity in G is certainly sent to the identity because everything is sent to the identity. And then we need to show that this morphism here, that this function here preserves composition. Well, if I have any two elements in G, and they both get sent to the identity, and then I compose them, I get the identity, or I compose them and they get sent to the identity. So this shows us that we get a group homomorphism. So does anyone have an idea about what the initial group could be? So the so a first guess might be to say the empty group, but there's no such thing as an empty group because by definition, any group contains at least the identity morphism, the identity element. And it turns out that actually maybe a better name for this would have been 0. So it turns out that the initial group is also the group with only the identity. Okay, so a LinkedIn user is asking for the full problem. So I told you what it means for an object in the category to be either initial or final. And I'm now going through some examples. So exactly, so 0 or E is also the initial group. And we'll play the same sort of game as before. We'll first think about what it means to write down a map of underlying sets between E and G. Well, by the definition of a group homomorphism, the identity element in 0 has to be sent to the identity element in G, but because in 0 we only have the identity element, then this element, then our morphism is already completely determined because this E has to be sent to the identity element in G. So E, by the group homomorphism definition, has to be sent to the identity element in G. And then again, you can just check that the identity composed with the identity as the identity. So if I send, if I take 2 copies of E and compose them, I get the identity and I send them to the identity in G, or I can send the identity to the identity in G twice and compose them and again get the identity in G. And right, so let me just mention the other 2 examples that we had. So in topological spaces, it's exactly the same as for sets. So the final object is a topological space with only 1 element. And the initial topological space is the empty topological space. And again, for vector spaces, the situation is completely analogous to the situation is completely analogous to groups. We can have that the 1 element vector space is both the initial and the final object. Except in this case, you might call it R0. And now we can finally move on to what I imagine many of you have been waiting for, is to see some more interesting universal constructions. So let's talk about product and coproduct. So whenever I write current brackets like this means that I'm talking about a doodad plus its dual, which is always denoted by co, in the same breath. So this will not make any sense to you quite yet, but once we've worked through some examples, I can get into this again. So I'll start off with the definition of products and coproduct. So first, some notation. So we'll fix some category. We'll fix some category C. And then first some notation. Right, so Henry asked whether one can also form a category of algebras. Absolutely. Right, so when you have an algebra, then you have a set together with two sets with 2 compositions on it. You have the addition and you have a vector space together with an extra multiplication on your vector space. And then in the category, your morphisms not only have to respect the vector space structure, they also have to respect the multiplication structure. And then this gives you a perfectly fine category. So let's introduce some notation. So given two objects, C0 and C1. So this here's a comma and this here's a 1. C0 and C1 in C. Then we can form two categories. We have a category which I denote by C over C0, C1, and a category which I denote by C under C0 and C1. And what are the objects? So the objects of this guy are diagrams of the following form. Yeah, got the arrows the wrong way around. There we go. Are diagrams of the following form. So you pick some object C and you pick two morphisms like this. And morphisms are diagrams which look as follows. So when you have two such objects, yes, I forgot my my dash there. Then these are morphisms from C to C prime, such that the two diagrams commute. And for this guy here, you just turn all the arrows around. So I can literally just copy everything like this. Copy. Oh, that didn't work out as nicely as I was hoping. Like this, and all I need to do is now just turn around all the arrows. So these arrows now point downwards. These arrows point downwards. And these arrows here also have to point downwards. Oops. Like this. All right, so now I've introduced some notation, and now I can give you the definition of coproducts and products. So with notation as above, the definition, the product of the two objects, C0 and C1, is the final object in C0 and C1, and the coproduct of C0 and C1 is the initial object in this other category that we defined. Right, so in category theory, whenever you put a co in front of something, you just turn all the arrows around. So now let's try to figure out what products and co-products are in our running examples. So one word of warning, I switched the order of things. So up here I was always doing the initial guy first, and then the final object, and here I switched it up. I'll always start off with the final object and then do the initial guy. Right, so so where were we? So I want to look at some examples. So let's say we had the example of sets. So I forgot to give the notation of the product and the coproduct. These have, of course, been denoted C0 cross C1, and the coproduct is usually denoted C0 this funny symbol here, C1. And at this point, I won't even ask you to guess what the product of two sets are, because both the name and the suggestion and the notation suggest that it's exactly what you think it is. The product of x and y in the categorical sense is precisely the product in the set theoretic sense. So what is it that we need to do? Well, we need to exhibit S cross Y as the final object of this category, right? So we need to consider exhibit S cross Y as what is called a span. So we need to write down two morphisms like this. Right, okay, so Michael already knows what the product and coproduct are. So let me just write down quickly what the what these maps are. So whenever a pair of element x, comma y, you send x to x and y to y. And now, whenever I have some other set, let's call it A, and let's draw this all in a different color so that we can remember that we drew this after x and y. So what was the thing? So let's have z go down to x and y. Call this f, and let's call this g. Then you can check that there exists a unique map like this, which I'll denote by f comma g, and f comma g sends any element of z to f of z times g of z. Right, and it's easily checked that this diagram commutes, because if I have an element z and I send it to fz gz, and then I project down, then I get precisely fz, and I get precisely gz. And moreover, this definition is forced upon us because if it were anything else, then it would just project down to the wrong things. And as Mike has already told us, the coproduct is the disjoint union. So the disjoint union is a little bit trickier than the product. So if x and y are disjoint, then the disjoint union can just be chosen to be the union of x and y. So I'll draw what's going on in pictures. So if x is a set that looks like this, let's call it a square, and let's have y be a set that looks like a circle, then the next disjoint union y is just going to be the union of these two guys together with the injections, like this. And then if I have any other map, z, so maybe take to be this triangle or something, and I have two maps, f and g to z. Well, now I want to write a new map, which I'll again call f comma g. And what is f comma g supposed to do? Well, if an element is in this part of our union, well, then I just look at the corresponding dot in x, and I just apply f to it. But if my element was in this part of my union, I just look at the corresponding point back here, and then I just apply g to it. Right. So then you can ask yourself, well, what about if, so let me just do this in words because it's a bit tedious and I want to finish at least all of these examples. So what happens if X and Y are not disjoint? So you can always force things to become disjoint, right? So recall that in category theory, any two objects in a category which are equivalent are considered to be equally good. So if I have, say, if any two bijective sets are considered to be equally good. So if I have two sets which overlap, I can always just find a second set which is bijective to one of the sets which isn't overlapping with my first set, and then I can just take the disjoint union of those two, and then I can just take the union of those two to get the disjoint union. So let's look at the situation. So again, for topological spaces, the situation is the same. So whenever you have two topological spaces, you can create the product topological space by looking at the product of the underlying sets, and then you take the product topology. And if you want to take the co-product, you take the disjoint union of the underlying sets, and you take the corresponding topology. But let's look at groups. So if I have two groups, then the product is again given by the categorical product is again given by the classical product that you probably already know and love. So here the multiplication of two elements is given element wise. So if I have G and G prime, and I want to multiply them with H and H prime, this is the same as just multiplying the first two and multiplying the second two. And then you can again check that the projection morphisms are again group homomorphisms, right? Because these projection maps manifestly preserve the composition, because if I have I'm sorry, I'm being stupid here. Let me just correct this quickly. So what we have there we go. So if I have two pairs GH and G prime H prime, and I want to multiply them, then I'll just multiply them component wise. And now we see as we project if I multiply them and then just isolate out the left bit, that's the same thing as isolating out the left two bits and then multiplying them, and the same thing on the right. So we certainly get a group homomorphism, and just like above, I could just go back and have a look at what happens in sets. So if I have a third group called L and two group homomorphisms, well, recall recall that a group homomorphism is a map of sets with some extra properties. So this means that if we have a group L together with two group homomorphisms like this, then we already know that there exists exactly one. We already know that there exists exactly one map of sets like this, and what we have to ask ourselves is whether or not this is a group homomorphism. And again, you can easily check that this is a group homomorphism because multiplication happens component-wise in G-COM-H. So let's spell this out quickly. So we have phi and psi. Right, so I have phi comma psi of L prime. Sorry. Multiplied is the same thing as phi sorry, I'm being very I should be more consistent with where I have a multiplication sign a lot. So let's just say we have multiplication signs here. L multiplied with L prime. Here we have psi L multiplied with L prime. But then these two guys were assumed to be group homomorphisms. So we get psi L multiplied with psi L prime, psi L multiplied with psi L prime. But then using this law up here, we then get psi L multiplied with psi L prime, psi L prime. Right, but this here is precisely phi comma psi of L times phi comma psi of L prime, like this. But then for the coproduct, I don't want to get into that today because we're already starting to run out of time, but you can look it up. It's the same thing as the free product. So what I want to end with today is what happens in vector spaces, because this is quite fun. This is quite interesting. Let's say I have two vector spaces. So Michael is asking, does the existence of product depend on the existence of initial objects? So the existence of a product is precisely equivalent to the existence of a final object in a certain category. Right, so you're asking precisely for the final object in this category here, which I defined further up. Right, so this here is so maybe your confusion with initial and final happened because here, so between here and here and here and here, I switched the order. So this top row here corresponds to the bottom row here, and this bottom row here corresponds to the top row here. And we were now looking at the final object in this category. So now let's say you have two vector spaces, then the product is given by then the product is given by what you think it is. It's exactly as for groups. So you're looking at, right, so this is something you all hopefully already know from linear algebra. The product of two vector spaces is again just given by looking at pairs of vectors, and you add and scale them component-wise. But then something surprising happens. The co-product is also given by V cross W. Right, so what does this mean? This means that we have to, right, so for the product, we have maps going down, but to exhibit V cross W as a co-product, we now have to look at maps going up. So what are these maps? So I send V to small v, 0, and I send W to W, to 0, W. And then if I have some further vector space, let's call it U, together with linear maps, again call them phi and psi, then I now have to produce some map phi, psi from V cross W to U. All right, well, let's see if we can reason ourselves to what it might be, a bit similar to how we're able to reason ourselves to what this universal map was in the case of products, right? So in the case of products, we said, okay, we know that a map of groups is a map of set with properties, and because we already know that the underlying set of the product of the two groups is a product of the underlying sets, there's at most one choice. And then we just need to check that this unique choice is indeed a group map. So here we can't do this anymore because the product of two sets is not the same as a co-product. But here's what we can do. We can reverse our reasoning. We can say we want, right? We already know that we want this here to be a to be linear, and this will already force our hand, because now we can do the following. We can say, let's say we've chosen two elements, V and W. Well, then we can rewrite this as follows. We can rewrite this as V comma 0 plus 0 comma W, like this, right? Because we're adding component-wise. So we know that V plus 0 is just going to give us back V, and 0 plus W is just going to give us back W. But because we want phi comma psi to be linear, as I said before, this forces a hand. This then tells us this, that we have no other choice but to define this here to be phi comma psi of V comma 0 plus phi comma psi of 0 comma W, and these two choices are also forced upon us, because recall that when we have, oops, wrong. Because recall when we have V and V, well, we sent this to V comma W, but we already know we know where we want to send V comma W, because we know that we want this triangle here to commute. So we see then that oops, I forgot to switch back my color. We see then that the left side has to be phi of V, and that the right side has to be psi of W. But this is so this is forced upon us by the two considerations that, firstly, we want a map to be linear, so we want it to preserve addition, and secondly, we want these two outer triangles to commute. Right? This was this condition. This was this condition that we had in the definition of these categories here. Right, and now we have to check. So we see that there is at most one choice for this map here to be linear. And now you can just check in general that if you have like phi comma psi of V plus V prime, W plus D W prime, well, we now know that this is sent to phi of V plus W prime. Oh, sorry, V plus V prime, psi of W plus W prime, phi of V prime, psi of W prime, but addition commutes vector spaces, so now you can just rewrite this as psi of V, phi of V plus psi of W plus psi of V prime plus phi of W prime. And this is then the same as, well, and then you can just and this is then phi comma psi of v comma w plus phi comma psi plus v prime of w prime, which is what we wanted to show, and then scaling is similar. Right, so just to review quickly, we defined what initial and final objects are in a category. And we saw that in set and topological spaces, the initial and final objects are different, but that in groups and vector spaces, the initial and final objects were the same. And then we decided to find product and co-product. And then we saw that in set and topological spaces, products and co-products were different. We saw that in the category of groups, products and co-products were different. But we saw that in vector spaces, not only are the initial and final objects the same, but also the product and co-product the same. And this is part of a general, very intriguing phenomenon called ambidexterity. Right, so if co and non-co corresponds to left and right, then having left and right coincide is some form of explains where the name ambidexterity comes from. And I just thought that this was an interesting pattern to end today's AMA on. And then next time I'll talk about more interesting universal properties. So are there any final questions before I sign off?
Any questions for Adrian? By the way, I take the opportunity to apologize for those who couldn't make it because I made a mistake by saying to people it was GMT instead of BST. So sorry for that. George has a question.
Yeah, so that's an excellent question. The tensor product is something I had saved for the next AMA. So I'll just leave you with this in 2 weeks. So I'll leave George with this cliffhanger. Hope you'll be able to handle the excitement.
Thank you. Yeah, so thank you so much, everyone. And we thank again Adrian for taking his time. I promise next time I will get the time zone correct. So apologies for that. So yeah, I will just end the stream. Before that, have a great rest of the day, wherever you are, or evening.